Hi guys. I wanted to take a minute to talk to you about the statistics project for this week, and it involves primarily the normal distribution. So, first of all, I wanted to share that if you click into one of these code cells, there's two kinds of cells in a Jupyter notebook. There's markdown cells that have text and equations sometimes and things like that. And if you want to edit the markdown, you double click the markdown cell and then you can edit the markdown content, which is basically text with indentation and stuff to make it look pretty. Um, if you hit Shift Enter in those cells, it'll render into HTML so you can see what the final rendered output actually looks like. But in a code cell, if you hit Shift Enter, it executes the code. So in this case, it's going to import some libraries and it's going to print out you did it when it's done. So there you go. I also want to point out that if you need help with a function that you don't know how it works or what it does, you can just type in the function name with a question mark and you'll get lots of lovely documentation describing how that function works. So that is sometimes helpful. The first function we're going to use is from the NumPy library. Notice it says from import NumPy as NP. So NP is just short for the NumPy library. And we're going to pull out the normal distribution from the random collection in the NumPy. So NumPy library, random collection of functions, normal distribution. It has three parameters: the position of the mean, the standard deviation, and the number of random numbers. And this guy produces an array of random numbers, 1,000 random numbers with a mean of 3 and a standard deviation of 0.5. So, and then the plotting library, which is called matplotlib, matplotlib gets pulled in as the plotting PL, the plotting library. You say pl.hist, and that creates a histogram. So you can increase, so if I execute this cell, you'll notice it made a histogram of the 1,000 random numbers. I could increase the number of random numbers, make it 10,000, and you'll see the histogram gets a little bit smoother. But let's work for the purposes of this exercise. Let's go ahead and put it back to 1,000 just to keep the numbers reasonable. And now you could, this is a normal distribution, sometimes called a bell curve or a Gaussian. The mathematical representation of that distribution is this guy, which looks pretty terrifying. But really, it just is a function, a mathematical function that represents the probability of having a number in any particular range here. So, and you could use calculus to figure out the probability of getting numbers between 3.5 and 4.5 or something like that. But my point is we can also use code. And so, for example, if I wanted to ask the question, how many of those random numbers were greater than 4? If I execute this cell, it tells me in this case there were 25. Of course, if I go back and run another batch of random numbers, I'll do that, and then I'll ask the question again. Now this time it was 26. So they're random numbers. So sometimes the number is going to jump around a little bit. Here I could ask, this gives me the actual list of numbers. This gives me the length of the list of numbers. And then this tells me if I take the length of the list of numbers, in other words, the number of numbers greater than 4 and divide by n, that's going to be an estimate of the probability of having a value greater than 4. N is the number of random numbers in the distribution. Length of the list, including only numbers that are greater than 4, is the number of numbers that are greater than 4. And so when I execute this guy, it tells me the probability is about 2.6%, 0.026 probability of being greater than 4, 0.027 is the probability of being less than 2. That turns out to be the probability of having a deviation from the mean of greater than 2 standard deviations, either in the positive or negative direction. And that number is normally around 5%. Of course, if I increase the number of random numbers, if I make this now 10,000, now I get 200 numbers, but the percentages stay about the same. There's my 200 random numbers greater than 4. And I end up with a probability of 222, 222, and 444. So I can, and if I want to increase the numbers even more, I get go to 100,000, and then we've got 2,000, and now we have 451. So there you see, by increasing the number of random numbers, I can improve the precision of my predictions. And that's a game we'll play sometimes. But anyway, that's how that works. The other thing I wanted to point out is this concept of normal plots. Normal plots are described in Alan Downey's book. It's called Thinking in Stats. And he describes the normal probability plot in there. And then he's got he uses his own ThinkStats functions to do it, but I'd like to have you guys use just the standard plotting functions that everybody uses, or a lot of people use with Python. So the way it works is you sort the random numbers in the distribution you have, and then you create a new distribution with a mean of 0 and a standard deviation of 1, but having the same size as the distribution of numbers that you have. You sort those guys, and then you plot those two sorted lists against one another. What you should get is a straight line, and you can see that with our random numbers, it is pretty straight. Let's go ahead. Actually, let me execute it. That's the line with the random numbers we just generated, and it's a pretty nice straight line. Not only that, it approximately has an intercept equal to the mean, and it has a slope equal to the standard deviation of the distribution. So now here's what we can do. Let's go ahead and find out the actual slope and standard deviation of a best fit line through our data and compare that to what we expect based on the theoretical concept of the normal plot, which should have a mean equal to it should have a intercept equal to the mean and a slope equal to the standard deviation. So we're going to use curve fit to do that. Now curve fit is a function we're going to be using a lot this semester. Basically, you give it a function, you give it some data, and it comes out with the parameters of the function. So the function we're going to use here is a linear function. We're going to pass it some data, and we're going to give it the parameters slope and intercept in that order. Curve fit returns two things. It returns an array of parameters, and it returns a two-dimensional array, a matrix of covariance values. The parameters, of course, are the slope and the intercept. So we just set slope, comma, intercept equal to parameters. That assigns the parameters to those individual variables. And the error in the slope and the error in the intercept come from the covariance matrix. It turns out those errors are the square root of the diagonal elements of the covariance matrix. Covariance is a 2 by 2 in this case, since there's two parameters. The diagonal elements are a two-element array. And you take the square root of those guys using the NumPy library. NumPy is nice because it can do things with arrays. So NumPy diag pulls out the diagonal elements of an array. MP square root, when you pass in an array, calculates the square root of every element of the array. Now there are only two in this case, and assigning those to the two variables dm and db can be done in a single assignment like this. And then we get the slope and the intercept. Now these guys are format strings. This says give me 3 decimal places of floating point number, give me 3 decimal places of floating point number. Number 0 would be the slope, number 1 would be the intercept. So this is just a way of formatting that output. And so if I execute this guy, it tells me the slope is 0.507, the intercept is 3.006, and you can see that it actually looks pretty darn good. It fits the data, and it lies pretty well along the line, the expected line. And here's how you plot the data, here's how you plot that expected line, and here's how you plot the fit. So here we've got the z's are the x values that come from the sorted normal distribution with a mean of 0 and a standard deviation of 1. And the x's, of course, are our data that we generated with a mean of 3 and a standard deviation of 0.5. And the fit linear function takes the z's and it calculates something like the x's, what we'd expect for the x's. So you can see how that works. If you have questions about how that works, let me know. The general plan is we're going to collect some data like z's and x's. we're going to have a model that we want to fit. We want to find out what these parameters are, in this case the slope and the intercept. And curve fit gives us the parameters and the covariance matrix, which we can use to estimate the uncertainty in the parameters, the error in the parameters. So that's the idea. So you have two exercises this week in statistics. One is to create a distribution of 10,000 random numbers with a given mean and standard deviation. And I'd like you to estimate the probability of getting a number greater than 35 from such a distribution. So we want to know what's the probability of seeing 35 or more from a distribution of random numbers with a mean of 25 and a standard deviation of 6. Does that make sense? So that's the idea. And the other one is to take the data from Project 1, the lab Project 1, and analyze it to try to work out the parameters of the Shockley model. Now the Shockley model is this guy. The current through the diode is dependent on the voltage across the diode. And I'm arguing here that in the lab, the currents we were measuring were milliamps or fractions of a milliamp, but that this current, I0, is probably more like microamps, something, tens of microamps maybe. But in any case, the exponential has to be much, much greater than the 1. So we can neglect the 1 here and analyze it as if this were the correct model. And we can solve this for the voltage across the diode, and we get an expression like this. Just take the log of both sides and fiddle around. You're going to get that. And you'll notice that we can break this out and rewrite it as a linear equation in the natural log of I. So the voltage across the diode is a constant times the natural log of I plus another constant. And we can go ahead and try to fit that. So what I want to do is pop down here. And I've got another notebook that I was using to analyze the data. Now the data I'm using here is the data I got from Tinkercad. I ran a simulation, and I posted another video about that. I ran a simulation of the lab we did, and it produced these numbers. This is I, the variable in the loop on the Arduino that was driving the current. That's the voltage measured on the wire going to the top of the resistor, the high voltage. The output of the amplifier basically is in1. In2 is the voltage drop across the diode, the voltage at the bottom of the resistor. So the difference between these two voltages allows me to compute the current through that resistor, which is also the current through the diode. So if I go back, let me go back here. So if I go down to the circuit diagram, oh, is it going to be in here though? Darn it. Yeah, I don't. Phooey. Hang on a second. I want to I just want to pull up that. Here it is. Okay, this is the circuit diagram I'm thinking of. In 1 is this voltage right here. In 2 is the voltage right here. So at the top and the bottom of this resistor. And for the purposes of argument, I'm assuming this resistor is like 150 ohms. So let's go back to the analysis here. And let's look at it. So if I just use the plotting library to plot the raw data in the CSV file. The CSV file, let me pull that up. This is the actual contents of the CSV file. I just copied and pasted this right out of Tinkercad. Of course, you can copy and paste right out of the Arduino IDE. You go to the serial monitor and just copy and paste right out of there. So when you load that into a pandas data frame, notice I'm importing pandas as PD. Pandas is the Python data analysis library. If you say pd.readcsv, it lets you pull a CSV file in, and then you have it as a data frame. If you just type the data frame, it will dump the data frame out to the terminal, out to the notebook, and you can see what the numbers are like. You can also say, please plot for me dataframe.i which is the first column in the data frame, versus data frame dot in1, which of course is the second column in the data frame, in1. And I want to use red dots for that, so R dot. And then also I versus in2, that's the voltage across the diode, of course measured in the Arduino units 0 to 1023, and I want to use blue dots. So this should be what your data look like. The red dot should just keep going up as you drive the thing harder and harder, but the blue dots should cap at the threshold voltage of the diode. And here, all I'm going to do is to convert those values from the Arduino to voltages. So 5 volts is the same as 1023 from the Arduino. So if I multiply by 5 divided by 1023, I should get the voltage across the diode. Here's the voltage at the top of the resistor. So now it's the same graph. Everything's the same, except instead of plotting Arduino values 0 to 1023, I'm plotting actual volts here. So this thing, you can see it's getting up right around 2 volts at the end. The voltage drive out of the amplifier is getting up, above 3.5 volts. Now our amplifier probably peaks at about 3.5 because we're using an LM324. In the Tinkercad, I had a 741, which doesn't have as much headroom as the 724. Anyway, here I'm calculating the current through the diode. Here I'm calculating the voltage drop across the resistor. And I'm plotting now in the Y direction the current, in the X direction the volts across the diode. And you can see the voltage goes up and up and up and nothing much happens. And then when you reach a certain threshold, boom, the current takes off. And that is the diode response we expect. Now the thing is, down here when the current is very small, if we're using a model that takes the log of the current, notice here here's my model, I take the log of the current, that's going to cause trouble because log of 0 is unfortunately not a good thing to try to do. So what I'm going to do is actually back off and I'm going to start the voltage around 1.75. So I figure out what drive number I need to be at to get the voltage up close to 175 to get close to threshold, and I'm going to focus our analysis on that region where the diode is actually going, right? Because that's where I know the current is big enough that I can actually measure it reliably. So here I'm looking at the voltage versus drive, and then for that same range, I'm looking at current versus voltage. So this is the part of the curve. I'm just looking at this part right here where the current is really going. I want to try to model that or fit that data with our model. So here's our model. It's A times the log of I plus B, right? That's the one we were looking at. I'm going to create a theoretical array of currents that goes from the minimum measured current to the maximum measured current with 20 numbers. So that means this is spanning the same range of currents, but it's a 20 element array with a uniform distribution of currents. And then I'm going to simply plot the theoretical current versus the output of my model. Here's my model. But I'm just going to throw in some numbers. Now what I did here was I looked at the data, I looked at the model, and I just tried to come up with some numbers that would get me in the ballpark. So after fiddling around a while, I realized that if I made A 0.03 and B around 2, I could get the model and the data to at least be in the same place in the plane, of the VI plane or whatever. And I just plotted those guys. So the data is the blue dots. The model with an A of 0.03 and a B of 2.1 is this curve. Obviously, that's a horrible fit. But what I can do is I can use those numbers where I'm in the ballpark and tell CurveFit to start looking here. The trouble is, if you don't give CurveFit a hint about where to begin looking, it'll go off into Never Never Land and never find a solution. But if you give it a hint about what the parameters are close to, then it can adjust and fiddle and get the parameters locked in with some reasonable numbers. So I did that. Here I am running CurveFit. I got the parameters in the covariance matrix. I assign A and B to the parameters, the error in A and the error in B to the same trick, square root of the diagonal elements of the covariance matrix. And then I print out the A and the error in A, B and the error in B. Now, this time I didn't specify any precision, but, and you can see it printed out a bunch of decimals. So in a report, you'd probably want to do like that other example and put some limits on the number of decimal places to display there. But what I want to point out is that even these parameters, 0.07 and 2.2 is what the curve fit ended up with. That looks a heck of a lot better than my crazy guess up here. But it's still not really wonderful because the curve is above the data here and goes below the data there. If I rewrite that and write it as a voltage on the horizontal axis and current on the vertical axis, you can see the model is not wonderful. It's deviating from the data at this point. It deviates from most of the data down here. So there's still something a little fishy. Now what I'd like to point out is that, where did I go? Here we go. This was the model we ended up with, and I claim here in the notebook that the problem is that we're not really measuring the junction voltage. We're measuring the voltage across the whole diode. And that means there's some inline resistance, some serial resistance that we have to include. So what I did is I added another term here, IR, which is the external voltage, the voltage we actually measure outside the diode. It's the diode voltage across the junction plus the drop across the internal resistance of the diode. And so I have a model that's A natural log I plus B plus the IR drop. So C is basically the same as that internal resistance. So I have a new model that has the bits we had before, A log I plus B, and an additional term, C times I, which takes into account some of that internal resistance. So what I want to do is go back and redo the model with that extra term, that C times I term. And I'm just going to initialize C as 0. And then do the curve fit again, but now with this more elaborate model. And now I get a value for A, B, and C. C works out to be about 6 ohms with this data. And then I replot the data, and look at that. That's beautiful. So it turns out that internal resistance really improved the performance of the model. It fits the data quite well here. Compare it to this without that internal resistance. There it is with the internal resistance. So it makes a big difference. So what I'd like you to do in your report, you don't have to worry about this intermediate model, the no R model. I would just jump straight to the internal resistance model with A, B, and C and see if you can get that guy to produce some reasonable results. Okay, so that's all I have for you. I hope that helps.